Moving along to back to the data directory, into this index 5 or so, we have image directory entry base reloc. And this is going to be the relocation information. So we're finally going to get at that information where I said, if it wants to be at base address 1 million, but it gets loaded at base address 2 million, you got to fix up all the constants. How the OS loader finds all the information to fix where all those constants are to fix them up is it's going to go to the base relocation information, and it's going to get forwarded on to a list of places that it needs to fix up if it moves the thing in memory. So relocations, that base entry reloc, basically points at an array. Points at one of these structures. No, I guess it's an array of these structures. Points at an array of these structures. Image-based relocation, it's got a virtual address, it's got a size, and then this type offset. Oh, wait, that's commented out, so never mind. But there is going to be something immediately after it that's of word size. So virtual address is basically going to say that this data structure corresponds to a given RVA range. And it'll only ever be hex 1000 range. So it'll be, virtual address will say like hex 1000. And what that'll tell you is that this particular data structure and all the data associated with it is going to be relevant from 1000 to 2000. And so the next data structure will say, I am applying to 2000. It'll be from 2000 to 3000. And we'll see why that is in a second. But the first order virtual address is just saying this structure applies to some chunk of memory range where it's going to have a list of everything that needs to be fixed inside of that memory range. Size of block is then how big is this list of stuff that has to be fixed in that memory range. And then the next thing after size of block is going to be a bunch of words that are the exact locations that have to be fixed after you do some calculation. So this is a terrible example right here, and I don't want to use that at all. It's to-do change me, so I'm gonna come up with a better example here on the fly. P-view still? Yes, good. I go with EXEs. Good. All right. So I just opened up one of my 32-bit things. So I just told you there's a data structure that has an RVA and a size, and then it's immediately followed by a bunch of entries that say, here's all the places you need to fix up. Now, these entries are of size word, so they're 2 bytes. And they're actually broken up not along byte boundaries. It turns out it's the first 4 bits, the topmost 4 bits, is specifying what type of entry it is, what kind of fix-up the OS should do. So the top 4 bits in this case, remember 4 bits to a hex character, so just this 3 basically is saying, I'm of type image rel-based high-low. So I don't really talk about the type because as far as you're concerned, everything's always going to be image-based rel-low. It's always going to start. All these words are going to start with a 3. So you can just think of chop the 3 off the top. And then what you need to do to get the location to fix up is you chop the 3 off the top. And then you say, take the rest, 001, and add it to the 1000 that this range applies to. And so it's 1001 is the RVA where it needs to fix something up. So there's a constant at RVA 1001 that the OS needs to fix up if it moves this thing in memory. There's a constant at 1007. There's a constant at 1016. So how I got that is I just chop off the first 3. I add this to the 1000. You'll see over here, CFF Explorer or P-view is just trying to do that for you. Right? So it just calculated. So now if I go down, so obviously if I'm chopping off the 3 and I've only got these 12 bits, right? 12 bits can only specify me, you know, from 1000 to 2000. 12 bits is hex 1000 worth of potential location. So I can go from 0 to FFF, right? Those are the only ranges that I can specify. So I can go from 0 to FFF plus hex 1000, and that'll give me everything in that range as a potential location. So how this works is you've got this first data structure that says I go from 1000 to 2000, and then you have to have more data structures that tell you, you know, I go from 2000 to 3000, and I go from 3000 to 4000, right? So there's going to be an array of these data structures that have what range they apply to, and then beneath that there's an array of, within that range, what specific locations does this apply to. So again, we just chop the 3 off and we see AC, so we go 2000 AC. That's what CFF P-view shows. I can show the same thing in CFF Explorer. It'll probably be trying even harder to fill that in for you. So again, you've got an array of things saying, I'm from 1,000 to 2,000, I'm from 2,000 to 3,000, so forth. And when you click on that, so you got 1,000 and you've got the size of these entries afterwards. And then these are the literal values, 3005, 3000D, 3002F. Chop the 3 off the top. And so when it puts it all together, we're in the 1000s right now. And so 1000 plus 5 is 1005. If we go down here, we're in the 2000s. 2000 plus 90 is 2090. Yes?
So what size, does that only fix up words?
Basically the type, yep, that's a good question. Basically the type is going to specify how big of a size it's fixing up and things like that. And so yes, in this case, it's fixing up a D word, right? So it's saying there's a 32-bit constant at this location. And so you moved me in memory, figure out what the diff is, and add that diff in to this constant. And so you're just applying that diff from where you want it to get loaded versus where you really got loaded. Apply that to 32-bit chunks. It can definitely be different. It's just then you'd have a different type, essentially. Yep. The type would say, all right, no, this is actually a 64-bit thing that needs to be fixed up.
Like part of that top nibble is also...
Yes, the top nibble is a type specifying essentially what size it's going to be fixing up, for instance. But as far as you're concerned, it's basically always going to be 32-bit. That said, let me go double check if I can confirm on a 64-bit thing that I see a different type. Never a good idea to go off the beaten path, unless it is. Yeah, sweet. A instead of 3, right? We've got a different type. So A's instead of 3's, type is dir. Let's see, can I change those? No, okay, doesn't matter. So anyways, A's instead of 3's, 64-bit relocations instead of 32-bit relocations, and apply that relocation at the address 2000 plus 148. 2148. Apply a relocation of size, whatever the type is. Yep, good question. Okie doke. That's pretty much it for relocations. Any other questions on relocations? We have some quizzes on this, but I'm probably going to keep going up through 12. I'm going to ask you to, come back and play through these rounds because, like I said, we want to make sure we get through all the PE material. I want to try to get through all the material by 1 o'clock at the latest. All right. So that's relocations. Let's see if I have anything else to say. Nope. Nope. Okay, one last thing on this. Just for my bailiwick, since I said that, some of the research and work I do is on memory integrity checking, which has to do with, what I was showing you over here. We've got attackers changing IATs, and we've got attackers changing EATs and things like that. So the stuff I work on is like look at it in memory and measure it and figure out whether it's being manipulated or not. And so we do things like, checking the data structures and the headers and stuff like that. But also we do things like checking the .text section, right? And so I said we've got the .text section. It's got all the code in there. That code potentially has hard-coded constants, which got changed when the thing got moved around in memory. So if I just do a hash of the .text section in memory and I do a hash of the .text section on disk, they're probably going to be different if the thing got relocated in memory, right? Because when you relocate it in memory, you're changing a bunch of constants. The hash is going to differ. So when we do memory verification of code in memory, for instance, we have to back on our end, we have to say, where did it get located in memory? And then we have to apply all of the relocations to a copy based on what we think the OS would have done. We take a copy off disk, apply all the relocations like we would think it would have basing it at that address in memory, and then we hash our reconstructed copy instead of hashing, just whatever happened to be in memory and sending it back. Well, we hash whatever's in memory and we send it back, but then we reconstruct based on where we think it should have been in memory, for instance. All right, so anyways, that's the only point about that. Threads.